Hello, my name is Nastia Naumova and I work in Artyom Zaganov Group. And today I will tell you about the example number 9 from USPEX calculations. And this is the 3D example. It's for molecular calculation of methane. So let's start. Once you copy the example file, that is what you will see. This is the input.txt file, the mol file, specific folder, reference folder, and the file to run the calculation. So let's start from the input file. What do we see here? Okay, and so first you need to specify the calculation method. So in our case, it's going to be like the USPEX run. The next string is the calculation type, where the first number is a dimension of your calculation. So in our case, it's three-dimensional calculation. Then the next number is to specify whether you want to calculate the molecular form or non-molecular. So in our case, it's methane molecule, so it's molecular type of the calculation. And the last one is to specify whether you want the variable composition or not. So we want to calculate just pure methane, so it's not variable composition, so it's going to be 0. The next string is the afterfrag that refers to the evolution operators. So that means that your operators will be updated automatically. So I suggest you always keep afterfrag equals to 1, unless you know what you're doing. Yes, the next string is the optimization type. So here we want to optimize the enthalpy. We can just type enthalpy, or we can type 1, so it's the same. Then atom types. Since we are going to calculate methane, this is going to be carbon and hydrogen. Also, you can write the atomic numbers, so that's going to be the same. Then the non-species. Non-species means how many molecules per unit cell you want to see in your calculations. So for methane, we want to calculate 4. That actually depends, of course, on your system. Then the next section is the population. So first string is about the population size. That string means how many individuals per generation you will have. So here it is 20. That's okay if you calculate just one type and it's not variable composition calculation. Initial population size, that string means how many individuals in the there will be in the first generation. Then the number of generations, that how many generations you will have in your calculation in total. And the stop criteria is, this parameter means after, let's say here, after 6 generations, when you will get the same results, your calculation will stop. If you will not find your best structure in all your 20 generations that you've set, so that means that your calculation will stop after the 20th generation. And this parameter, reopt-old, it means that you want to re-optimize the structures that you got from your previous generations. Then in our input, we see the variation operators section. And this is just like some variation operators. The first one is, okay, that doesn't actually mean. I suggest you to leave just all these variation operators as they are for all your calculations, because they are updated during each generation if you set the afterfrag equals to 1. So just leave them as they are. Then the constraints section. So ion distances, actually you don't need to specify ion distances for this explicit calculation, because the USPEX have some default values for ion distances. But this parameter means the minimal distances between the atoms. So if you will somehow generate a structure where the distances between atoms are less than listed here, the structure will be killed. Yes, and you see here the matrix 2 by 2 because you have like two types of atoms. So that means that the distance between two carbons, let's say, will be at least 2 angstrom, and between carbon and hydrogen will be at least 1.2 angstrom, and between two hydrogens are 0.7 angstrom. Yes, the next parameter, the mole centers, it is obligatory. You need to set it, and this parameter means the distance between the centers of two molecules in your unit cell. So here for methane we set 2.8 angstroms. Yes, and that's going to be enough. Then the next section is the details of the ab initio calculations. So here we come to our code that we are going to use with USPEX. And here in our case, we are going to use WASP. So 1 means WASP here. And you see that here are 1, 2, 3, 4, 5 steps. So in all 5 steps, we are going to use WASP. So we need to type 5 times 1. And the next one is the K resolution. That's a resolution of K points that we want to set for our each WASP run. So the first one is the less accurate one, and the last one where we see like 0.09, it's the most accurate one. Then the command is executable. That's how we're going to run our calculations. And the last sections are the number of parallel calcs. That means how many parallel calculations do we want to have in our USPEX run. Then the which cluster. Here we have just 3 options, 0, 1, or 2. If we set 0, that means that we will run locally with no parallelization. If we set 1, that means that we will run our calculation locally, but we can set some parallelization in the submission folder. And if we type 2, that means that we want to run it remotely. And the last section is external pressure. That is in gigapascal. So here we want to calculate our structures at 20 gigapascal. Yes. So what else do we have here? This is the mol file. Mol file is needed for molecular calculations. So let me describe you how we need to make the mol file. So usually the mol files, they are made of from XYZ files. So here on the screen you see like the good example of correct XYZ file for conversion to mol file. So you hear that you see here that the methane molecule, it is like the whole molecule. It's not made of parts. And here is a bad example of XYZ file. You see that here is also methane molecule, but it was converted from postcar in the wrong way, that all the hydrogen atoms, they are not connected to carbon. So it was converted from the postcar of this type of postcar where the carbon atom, it occasionally was in the angle. So that's why we need to make the mol file from the whole molecule. Yes, and what else do we have here? This is the reference folder. That's a folder where you have all the results of your calculation. So we will come to it later. And the specific folder. So let's go to specific folder. What do we have here? In specific folder, you see that we have all the incar files and podcar files for our WASP runs. As you remember, in the input text there, we specified that we are going to have 5 VASP runs. So here we must have 5 incars. So let's see what is the difference between all of them. So the first incar is always the less accurate one. So the precision here always should be set to low. And also what is important here, we don't set the cutoff here. In the first 2 incars, we don't set the cutoff because we just want to relax our bad structure that USPEX generated to some minima. And then we want to recalculate them by means of other incars more precisely. So the first 2 incars are absolutely not precise. They are needed just for some relaxations. Yeah, so here is the first one, here is the second one. So you see here that we just increase the accuracy a little bit. Then what is going on here? So this is in incar 3. You see that here the yen cut appears. So as for me, it's a little bit high. I would set it for the first time for about, I don't know, let's say 400 or even 350. Yes, the next one, this is incar 4. So you see here that the precision goes higher. And the last one, the incar 5, we need it just for some accurate recalculation of the energy that USPEX will take, and it will calculate the convex hull for all the structures. So the last incar is always for some energy recalculation. It's not for relaxation. Yeah, so here is our specific folder. And also we have like potentials here. Of course, we must have all the potentials for all items that should be named. If we are calculating methane molecule, we must have the podcar for carbon and podcar for hydrogen molecule. And the final step is to run our calculation. How we can do it? So first of all, once you copied your example folder, you need to generate all the rest folders. To do that, you need to type USPEX -G. And you see that some new folders, they were generated. That is anti-seeds folder, we don't need it now. Seeds folder, where you can put seeds, we also don't need it now. And the submission folder, this one we need. So the submission folder we need for this section, for which cluster. If we have which cluster equals to 1, that means that we are going to submit our job locally. And for this local submission, we need to specify the submission file. We can do it in submission folder, in submit job. Okay, and submit job local. Submit job local. So here you see that we have, let's say in our cluster we have SBatch. That's why it was generated with SBatch. So that is the correct file. That's it. And to run our calculation, what we need to do is to nohub this submission file. There is sh. Yes, and what do we see? All the information about our run is written to a log file. So it started. Yes, here we see the ion distances that were in our input. This is the volume that was calculated from our mol1 file. And then we see that USPEX started to generate structures. So it this structure has some symmetries, and you see that everywhere here we have just 4 molecules per unit cell. So that's it. So while it's generating, I want to show you one more thing. So it's an input file. If we want to calculate the, let's say, methane, not just for 4 molecules per unit cell, what we can do, we don't change this 310 type of the calculation, but we change here. We change the non-species. We set it to 1. And also we need to add the min at section and max at section. So let's say we want to calculate methane with, we want to find some configuration of methane, let's say from 1 molecule in the unit cell. So that's going to be min at, up to, let's say, I don't know, 6 molecules per unit cell. And here we type max at. So by means of this, we will get the variable composition. Okay. Yes. So let's go to reference section and see what do we have here. So from reference section, that's going to be your results 1 folder, where you will get all your results. What is important here? So let's see the best individuals. So in best individuals, we see that our calculation was running during the 8 generations. And in the 8th generation, it found like the best structure. This ID is 176, so we can find its postcard. And here we see like all the best structures from each generation. This is the one important thing. So to find its postcard, we need to go to, let's say, best gather postcards or just gather postcards and try to find it by its number, by its ID. And another important thing here is this E-series. E-series, this is the PDF file where you can have a look how your energy was converged during the USPEX run. So you see your runs, it is updated during all the generations. So in every generation you will get the new E-series file. And this is from the last 8th generation. You see that in the first step of relaxations, first 2 steps of relaxation, the convergence was not very good. Then it became better and better. And finally, it was like the straight line. Yeah, so I think that is pretty much it. That's everything that I wanted to tell you. So yeah, that's it.